In this video, we will be talking about classifying our singularities. So Laurent expansion allows singularities of functions to be categorized as poles, removable singularities, or essential singularities. This is our overview slide, which we'll spend about 5 minutes on before going over these topics in more detail and with more examples. The first type of singularity we will talk about are poles. So imagine we have a point z equals a. That's a singularity of our function f of z. If the most negative term in the Laurent series expansion around the singular point is minus m, the singularity is called a pole of order m. So for example, if we have f of z equals 1 minus z over a, so the most negative point around the expansion of the singular point, that's the z minus a. A is our singular point. And it's a simple pole because the order on the exponent here, m, is equal to 1. If we have f of z equals 1 over z minus a cubed, then this will be a pole of order 3. If we already have a Laurent series expansion for a function, it's easy to determine the order of the pole. But if we don't already have a Laurent series expansion, sometimes it's easier to use this formula. It's not applicable to all functions, but it is applicable to many functions and their poles. So notice a pole of order m at z equals a, we can multiply by a factor of z minus a to the m, and we'll get rid of that divergence. That is, we can now look at the limit as z approaches a of f of z, z minus a to the m. If f of z has a pole of order m, we get rid of that singularity. We can then look at the limit as z approaches a, and if it's a finite value, then we will know what the order is. It's basically whatever this exponent is here, m. Next, we will talk about removable singularities where the function does not diverge as we approach the singularity. So it's possible we have a function that appears to have a pole, but on closer examination does not. Our example is f of z equals sine of z over z. So you can see we have a singularity at z equals 0. However, the limit as z approaches infinity of sine of z over z, using L'Hopital's rule or at inspection if you graph this function, will equal to 1. So this is called a removable singularity. The function has a singularity at the point z equals 0 because the denominator goes to 0, but the Laurent expansion around z equals 0 has no negative terms. This type of singularity is called removable because the function does not diverge as we approach the singularity. And finally, we have the essential singularity where the function diverges at the singularity, unlike the removable singularity. The Laurent expansion for a function about an essential singularity will have an infinite number of negative terms, and our example is e to the 1 over z. It has a singularity at z equals 0, and this function goes to infinity as z goes to 0. That concludes our overview. We'll come back over here and take a closer look at poles now. If we have a point z equals a that is a singularity of a function f of z, we can classify it according to the order of its pole. If the most negative term in the Laurent series expansion around the singular point is minus m, so you see that we take the Laurent expansion around using our singular point where we center our expansion. If the most negative exponent is minus m, the singularity is called a pole of order m. And a pole of order 1 is often called a simple pole. And our first example is f of z is equal to 1 over z minus a. So z naught equals a is a simple pole because that's where our function diverges. Since the largest negative exponent is equal to 1, z minus 1 to the first power, it is a simple pole. Here we have f of z equals 1 over z minus a cubed. Now in our Laurent series expansion, which only has one term, our most negative exponent is 3, which means a is a pole of order 3. Our next example is z plus 1 over z cubed times z squared plus 1. Factoring out the z squared plus 1, remember we're doing complex analysis here, so we can factor that into z plus I and z minus I. Here we have z equals 0 is a pole of order 3. You can see how we have division by 0, so the function will diverge. For z equals -1 and z equals 1, those are both simple poles. Our next example is f of z equals z squared minus 2z plus 3 over z minus 2, and we do have a simple pole at z equals 2. We do want to be careful that nothing in our numerator can cancel with our denominator, so I went ahead and did the Laurent series expansion for this function at z naught equals 2. And what I did is I wrote down the function z squared minus 2z plus 3 over z minus 2. I notice in the numerator I can factor out my z and I get a z times z minus 2 plus 3 over z minus 2. I then separate my fractions. I have these two cancel and I'm left with z, and over here I get 3 over z minus 2. This here is not in my form, it's not expanded around z equals 2, but I can introduce my minus 2 and then add a 2. Remember, in my Laurent series expansion, it's okay to have coefficients, but my z terms, we want to expand it around a z naught. So here I have 2 plus z minus 2 plus 3 over z minus 2. This is my Laurent series expansion. You can see 2 is my, this is my most negative exponent, and it's equal to 1. So our simple pole is z equals 2. Our next topic is determining the order of a pole. So when f of z is in Laurent series expansion, it's easy to find the order of the pole. You look for the most negative exponent. If it's not in Laurent expansion form, we notice that a pole of order m at z equals a multiplied by a factor z minus a to the m will get rid of the divergence. That is, the limit as z approaches a of f of z, z minus a to the m gives us a finite value. Then whatever this value of m is, that's the exponent that we need to use to take this limit to get a finite value. This value of m is going to be the order of our pole. For example, we can consider f of z equals z divided by cosine z minus 1. And here there are singularities everywhere, right? Whenever cosine z equals 1, there's a singularity. We will consider z equals 0. Again, because cosine's periodic, every 2 pi, you're going to get 1. But let's consider z equals 0. We can see the function diverges as we approach z equals 0 because cosine's equal to 1, and then in the denominator we have 0. But we want to look at the limit as z approaches 0 of z over cosine z minus 1. Since as z approaches 0, the numerator and the denominator are both equal to 0, we need to apply L'Hopital's rule. So on top, the derivative of z is 1, and on bottom, the derivative of cosine z minus 1 is simply minus sine of z. The limit then, as we approach 0, is 1 over, or negative 1 over 0. So our limit is negative infinity, so we definitely have a function that diverges as we approach z equals 0. To find the order of the pole, we're going to multiply our function by z minus 0. 0 here is where we have our singularity. So we're going to multiply by z minus 0 until the limit does not diverge. So here we have limit as z approaches infinity of z over cosine z minus 1. We're going to multiply by z minus 0, and we're going to get z squared cosine z minus 1, which is the limit as z approaches 0. Now, again, as we approach 0, we're going to get 0 on top. Cosine of 0 is 1, so we get 1 on bottom, so we'll use L'Hopital's rule and take the derivative on top, which is 2z, the derivative on bottom, which is minus sine z. Now the limit as z approaches 0 of this function is going to be 0 over 0 again. So we take L'Hopital's rule one more time, and the derivative of what's on top is 2z. The derivative on what's on bottom is minus cosine z, so the limit as z approaches 0, this on the bottom becomes 1, is equal to negative 2. So finally, after how many uses of L'Hopital? Well, we multiplied by z minus 0 once, and then we used L'Hopital's rule, twice. 2 uses of L'Hopital's rule, we get something that does not diverge. We had to multiply by z minus 0 once, which means that z minus 0 is a simple pole. Our next example is f of z equals z plus 1 over z cubed z squared plus 1. I'll start by factoring this z squared plus 1 to z plus I and z minus I, and then I can note that we have singularities at z equals 0, z equals I, and z equals minus I. I will start by verifying the divergence at z equals 0. So the limit as z approaches 0 is 1 over 0. So it's not a 0 over 0, so you can't use L'Hopital. It's 1 over 0, so we are stuck with a function that diverges. So now let's look at the order of the z equals 0 pole. Using our method over here, we're going to multiply by z minus a. So z minus a, our singularity is 0. So z minus 0, we're going to multiply z plus 1, z cubed, z squared plus 1. This z will cancel with one of these z's. So we're left with z plus 1, z squared plus 1. When we take the limit as z approaches 0, we still get 1 over 0. We still diverge. Because we still diverge, we're going to multiply this function now, my z plus 1, z squared plus 1, by another z minus 0 term. That will cancel out one of these z's, and we get z plus 1 over z squared plus 1. Take the limit as z approaches 0. We still get 1 over 0. We still have a divergent function. Finally, when we multiply this 1 plus z times z squared plus 1, now by another factor z minus 0, this will cancel, and we're left with z plus 1 over z squared plus 1. Now when we take the limit as z approaches 0, we get 1 over 1. We had to multiply our function by 3 factors of z minus 0. In other words, z minus 0 to the third. That means z equals 0 is a pole of order 3. We can do something similar for z equals I, our next pole. We take the limit as z approaches I, our function z plus 1, and I used this factored version here where we factored out z squared plus 1 to z plus I, z minus I, z cubed, z plus I, z minus I. When we plug in I, here we get 0, and on top we're going to get I plus 1. So it's not 0 over 0. We can't use L'Hopital, but we have something divided by 0, so that's divergent. We take our function then and then multiply by a factor of z minus a, and a being I. So here we have z minus I. We look at the limit as we approach z equals I. So we'll have z plus I, z cubed, z plus I here. Our z minus I gets canceled out. So we have the limit as z approaches I of 1 plus I on top. Our I cubed times 2I on bottom. So this is some number, but in particular, it's not infinity, so it no longer diverges. We had to multiply by one factor z minus I, which makes I a simple pole. Similarly, we can find that minus I is also a simple pole. Our next topic are removable singularities versus essential singularities. A removable singularity is when the function does not diverge as we approach the singularity. You notice in the previous example, when we were looking at our singularities, we verified that our function would diverge. So it's possible to have a function that appears to have a pole, but on closer examination does not. Our first example is f of z equals sine of z over z. When you take the limit as z approaches 0 of sine of z over z, well, sine of 0 is 0, and then on the bottom you have 0. So 0 over 0, that's a form that you can use L'Hopital's rule. So we'll take the derivative of what's on top and get cosine of z. The derivative on what's on bottom of z gives us 1. Now we can take the limit again as z approaches 0, and we get cosine of 0, which is 1. 1 over 1 is equal to 1. So the limit of sine z over z as it approaches 0 is equal to 1. So the function has a singularity at z equals 0 because the denominator goes to 0. But because the function is not divergent, you will see the Laurent expansion around z equals 0 has no negative terms. It's analytic. So this type of singularity is called removable because the function does not diverge as we approach the singularity. Another example is the function f of z equals 1 minus cosine z over z squared. Again, z equals 0 is a singularity because the denominator goes to 0. But if we take the limit as z approaches 0 of 1 minus cosine z over z squared, plugging in 0, cosine 0 is 1, so we get 0 on the top, and then 0 squared is 0, so we have the numerator and denominator are both 0. 0 over 0 means we can use L'Hopital's rule. We take the derivative of what's on top, which is sine of z, derivative of what's on bottom is 2z, and now we take the limit as we approach 0. We still get 0 over 0, so we take L'Hopital's rule again. What we get on top is cosine z, what we get on bottom is 2. Now when we take the limit as z approaches 0, we get 1 over 2, so it's 1/2. That means this function does not diverge. So z equals 0 is a removable singularity of this function as well. We are going to contrast those examples of removable singularity with our examples of essential singularities, and that's where the function diverges at the singularity. So the Laurent expansion for a function about an essential singular point will have an infinite number of negative n terms. Our example is f of z equals e to the 1 over z. You can see there's a singularity at 0 because 1 over z will give us a division by 0. But let's look at the limit as z approaches infinity of e to the 1 over z, and that would be, well, here we have 1 over z is infinity, so it's e to the infinity, which will be equal to infinity. And you can see we can't just multiply by z minus 0 as we did for the removable singularity and get rid of the singularity of e to the 1 over z. No matter how many times we multiply by z minus 0, this part is always going to go to infinity. So in this case, this z equals 0 is an essential singularity for this function. To review what we discussed classification of singularities. Laurent series expansions allow singularities of functions to be categorized as poles, removable singularities, or essential singularities. And when we have a pole, we classify them by the order of the most negative exponent. So the most negative exponent is called the order of the pole, and if we have a pole of order 1, we call that a simple pole, and we did our examples. Next, we determine the order of a pole. We can look, of course, if we have the Laurent series expansion, we could just look at the expansion, but if we don't have a series in Laurent form, we can just multiply our function by z minus a m times until we finally get a function that converges to a finite value, and then the number of times we multiply our function by z minus a will tell us what the order of our pole is. The last two topics we talked about were removable versus essential singularities. A removable singularity is a function that does not diverge as we approach the singularity, and this was our example. F of z equals sine of z over z. There's a singularity at z equals 0 because we have division by 0, but if we look at the limit as we approach infinity, we see that the limit will equal to 1, and you can see that either by graphing or repeated use of L'Hopital. And what we see, even though we have the singularity, the Laurent expansion will have no negative terms because the function is an analytic everywhere, so it kind of devolves into a Taylor series. We contrast this with an essential singularity where the function diverges at the singularity, and the Laurent expansion for the function about an essential singularity point will have an infinite number of negative n terms, and we have our example here. So that was it for this video. Thank you for watching.